Welcome back to ECE 441A, 541A. Thank you for watching or listening and looking at the notes. Today what I want to do is remind you that a week from Monday, your lab number 1 report is due, and that should be fairly well scripted in terms of fill in the blanks for what you need to do from the procedural steps in lab number 1. You should watch for homework number 3 on D2L. Hopefully that will be coming shortly, and that will be discussing or dealing with topics since exam number 1. And just so that it's on everybody's mind, we do have exam number 2 scheduled, and it is scheduled for Friday the 21st of October. What I want to do today is actually develop techniques for converting between system representations. We've done that before, but there was a question at one point, how do we go from Statespace, from transfer function to Statespace, and that's what we want to discuss today. And we will look at one particular representation, and that is an input feed-forward Statespace representation. After we develop the process, you won't have to work through that process necessarily again. You will simply need to know how to interpret what we've built in terms of how to go from a given transfer function to a state space representation. We'll illustrate that with a strictly proper transfer function. Strictly proper meaning that the degree of the numerator is strictly less than the degree of the denominator. And then if we do have a transfer function that's not strictly proper but is instead simply proper, where the numerator degree is the same order as the denominator degree, we'll discuss how to handle that, essentially some long division, to convert that into a constant plus a strictly proper transfer function. And we'll use that then, or the techniques that we talk about today, in terms of going from a strictly proper transfer function into a state space representation, and then it's turn the crank in terms of obtaining that state space representation. We want to then convert between system representations, and we have these 4 different ways of modeling or representing a system. We have a transfer function, we have differential equations, we have block diagrams. Those are the all-integrator block diagrams in the time domain, or they are the S-domain, frequency domain versions of those block diagrams. And we also have state space representations. I hope that you remember that we do have a way of going from state space to the transfer function. That's actually what we've been calling our first cheer, and that's where we now can obtain this transfer function g of s as c times si minus a inverse b plus d. So if we have our state space matrices A, B, C, and D, we can now plug them into this equation, or cheer 1, to obtain a transfer function. What we want to do today is actually figure out how can we go from a transfer function back to, or to, a state space representation, and we will actually show how to find a transfer function state space representation conversion by first looking at how to convert a transfer function into a differential equation, or a set of differential equations, take those differential equations into a block diagram, then by assigning state variables as the outputs of our integrators, we can immediately find a state space representation. Now that we've gone that path, we now have a connection between a transfer function and a state space representation, and we can now simply bypass that process and use the results to go directly from a transfer function to a state space representation. We know how to go this way. I hope you remember that that's Mason's gain. or can be, and it could be block diagram algebra. And you know how to go from a state space representation to a block diagram by simply defining the inputs of integrators as your x primes, and then the outputs will be the state variables, and then you interconnect it as described in the state space representation. Today what we want to talk about, though, is going from a transfer function to the differential equation, then to the block diagram, then to a state space representation. That's what we want to do. We're assuming we have a transfer function, which is some ratio of output to input. We're going between the input u of s and the output y of s. And what we want to do is obtain a linear state space representation. And remember that I'm saying a because state space representations are not unique. That's why there's the A. It's not obtain the linear state space representation. It's obtain a state space or a linear state space representation. And as I said above, the way that we will do that is we will go from transfer function to differential equation. That's the cross multiplication step. Then here is the step that will take us the most time and probably will provide you with a little bit more concentration effort to understand how we're going from differential equations to block diagram. But once we have the block diagram, it's pretty straightforward to simply label the outputs of the integrators as your state variables to obtain our state space representation. Let's get started with this process. And once we have this, then we can immediately, just in a sense, jump over all of that and go from transfer function to state space, knowing where the parameters in our transfer function are relative to where they end up in this state space representation that we will develop today. Starting then with the transfer function, and we will model this in terms of unknown variables. It's now the output over the input, and let's now say that our numerator is b sub 2 s squared plus b1 s plus b sub 0. The subscripts then referring to the power of s, and then we have s cubed plus a sub 2 s squared plus a sub 1 s plus a sub 0, and you can think of this as being a ratio of a numerator polynomial to a denominator polynomial. One comment that I need to make is that we are assuming that the highest power coefficient on the denominator polynomial has been normalized to 1, meaning we factored out whatever was in front of s cubed and incorporated that into our numerator coefficients. And you may see this referred to or described as a monic polynomial, and that means that we now have normalized the leading coefficient to 1, or if that was a 6, we factored that out from every term in the denominator, and we divide all of our original numerator coefficients by 6 to now make our denominator coefficient or polynomial monic. What we now want to do with this transfer function is obtain the differential equation that relates the output y of t to the input u of t, or we are now going back into the time domain so that we can start building an all-integrator block diagram. So we're asking the question, what is the differential equation relating the output y of t and the input u of t? Which I hope you remember that we can obtain that simply by cross-multiplying to essentially clear the fractions. We can find an equation for the output in the frequency domain, y of s. That's now t of s times u of s, where t of s is this ratio of n of s to d of s. We now have n of s over d of s times u of s, and what we want to do is get rid of that d of s in the denominator. Let's then multiply both sides through by d of s, and we now have d of s operating on y of s. Again, d of s is this frequency domain polynomial in s, equaling the numerator polynomial times the Laplace transform of the input. Using the parameterized polynomials that we introduced above, we then have, and remember that d was monic, so we have s cubed plus a sub 2 s squared plus a1s plus a sub 0. That is then multiplying y of s, and that's equal to b sub 2 s squared plus b1s plus b sub 0 u of s. And make sure that it's clear that the denominator polynomial order, which is 3, is strictly larger than the numerator polynomial, which was 2. And that allows us now to continue or proceed using this technique. It's now trivial, really, to take this into the time domain. That's a frequency domain relationship between the Laplace transform of the output and the Laplace transform of the input. Now we simply have to remember that multiplication by s in the frequency domain corresponds to differentiation in the time domain. If we now have s cubed operating on y, now we have the third derivative of the output variable with respect to time, plus a sub 2 y double prime of t plus a1 y prime of t plus a sub 0 y of t, and that's now equal to b sub 2 u double prime of t plus b1 u prime of t plus b sub 0 u of t. And what we've done before is we actually usually solve this for the highest powered derivative, which is what we will do. So in this next step, I'm doing really two things. I'm combining two steps. I'm isolating y triple prime on the left and moving everything else onto the right, but I'm also at the same time going to integrate both sides of this equation one time. Let me then say that I'm going to integrate one time, and in so doing, if I integrate y triple prime once, I hope it's clear that I end up with the second derivative of y. And now I've moved all the y terms to the right-hand side, and I've integrated every term one time. I now have a minus a sub 2 y prime of t minus an a1 y of t minus an a sub 0 integral, and a sub 0 is a constant, let's say y of t d tau from 0 up to t. That accounts for all of my output variables. Now I have to integrate my input terms. I have b sub 2 u prime of t plus b1 u of t, and since they already were on the right hand side, I don't have a negative sign in front of any of these, plus this b sub 0 integral of u of tau d tau from 0 to t. And what I really want to do is combine that integral so that I don't have to worry about having two different integrators in my block diagram. I'm integrating both y and u with one integration. Let me then just say that I now can rewrite this as y double prime is minus a sub 2 y prime minus a sub 1 y of t and plus b sub 2 u prime. And maybe what I should do is start combining, and let me just go ahead and do that. I'm going to start associating these powers or derivative terms with each other. So I now have minus a sub 2 y prime. Let me locate that close to b sub 2 u prime. Then I have a minus a1 y of t plus a b1 u of t. And now, doing what I suggested I was going to do, let me go ahead and combine, and now let me pull those coefficients inside. I now have this integral from 0 to t of b sub 0 u of tau minus a sub 0 y of tau d tau. I haven't done anything other than rearrange where the y's and the u's and the different differentiated variables are located. And really what I'm trying to do is find an expression for y of t. And I started with the third derivative of y, and that was a third order differential equation. You would expect that I'm going to need to have three integrals in my block diagram. So let me now integrate again. And that now tells me that I have y prime of t on the left. I have a minus a sub 2y, and I'm going to forget some of the arguments, plus b sub 2u. Then I'm going to actually need to worry about nesting some of these integrals, meaning I already have b0u minus a0y integrated once. Now I'm going to integrate that twice, but I'm also integrating a1y plus b1u one time. So let me say that I'm now saying plus the integral of b1u, and let me, if you wanted to keep track of these variables of integration, let me call that tau hat minus a1y of tau hat. Now I haven't closed that bracket, but I now need to incorporate, so this is still within the square bracket, and I now have the original, or the first integral, the integral from 0 to t again of b sub 0 u of tau minus a sub 0 y of tau. That's d tau, and now I can close my square bracket. Maybe I should make those stand out a little bit. And now this is d tau hat. And this last integral is now enclosed or contained within this middle integral, or the integral on the middle line. And if we do that step one more time, if we integrate a third time, I will now end up with really what I wanted, which was my output by itself without any derivatives on the left. This is now equal to the integral, and now I'm going to change brackets. I'm going to do a curly bracket, b sub 2 u of, let's say, tau tilde, again changing the variable. So there's b sub 2 u tilde minus a sub 2 y tilde. I'm going to keep going with inside that integral. I now have plus the integral, and before I'd put that in red, and this was now going to be b1 u of tau hat minus a sub 1 y of tau hat. Again, I haven't closed up that square bracket yet, and I now say plus this integral in the normal parenthesis, b sub 0 u of tau minus a sub 0 y of tau d tau. I can now close up my square bracket, and maybe I will go ahead and change the color. just to make it maybe a little bit cleaner. And now this is the last differential, and that's d tau tilde. That's what I want, is this sort of nested set of integrals. And what I want to now do is use this expression to create a block diagram. And what I'm going to do is I'm going to start with the output on the right-hand side in my block diagram and say, okay, I want to now label the outputs of my integrators as state variables, which means that I want to take all of this that's included here, and that's going all the way to the end, and I'm going to call that x1 of t. So that now I have in my block diagram y of t coming out of an integral, which is right here, and that integral now, I'm calling the output of that integral x1 of t. Which means that if I'm assuming that I have my input signal and output signal available to me, I have y of t, which I've just drawn there, and now let me assume that I have my my input signal u of t available. Now what I want to do is go slightly inside, or to the inside of that first integration, and work with what's inside the curly brackets. And what's inside the curly brackets, if the output of that integrator is x1, hopefully it's clear that the input of that integrator must be the derivative of x1, meaning right here is x1 prime of t. And making up x1 prime of t, if you look at what we have a b sub 2 times u. So let me take u and scale that by b sub 2. Then what do I have? Then I have a minus a sub 2y and I have y available here. And then what do I have? Well, then I have this output of this integrator, which I'm going to label as another state variable. I'm going to call that x sub 2 of t, meaning right here is x sub 2 of t. So that now I've created x1 prime. The output of that summing junction on the right is b sub 2u minus a sub 2y plus x sub 2, which is the output of that middle integrator. And now I can repeat that process. I can say, oh, I can now build the input to that integrator. I know if the output of that integrator is x sub 2, the input must be x2 prime, which is now what is enclosed in the square brackets that are red. And we do the same thing that we did before. This is now going to be something coming into a summing junction to produce x2 prime, and in fact it's b1 that scales u. Then we scale y with a minus a1, and here's y. And like we've done before, now what we do is we define the output of this last integrator to be another state variable, x sub 3. We knew that we were dealing with a third order system, so that now this particular input, or the last signal coming into that summing junction, is x sub 3. But that's an output of an integrator, which means that we need one more integrator, There's our three integrators making up this third order system. We only have one more step to make, or to work through, and that is to create the first derivative of x sub 3, which is the input to that leftmost integrator. And that is now found inside the normal parentheses, or the argument to our last integral term in that expression for our output y. So x sub 3 prime is now b sub 0. It's going to be again created by combining signals. One of those signals is made up of a scaled input, and the input is scaled by b sub 0, and another signal making up x sub 3 prime, which is the argument of the integral. That last integral is minus a sub 0 y. And there is our block diagram. That's our all-integrator block diagram that resulted from this transfer function that had a monic denominator. We cross-multiplied, we took it into the time domain, and we just started integrating both sides of that equation until we had integrated the left side, which contained the highest powered derivative, until it ended up being just y of t. We now have a block diagram. It's already really labeled for us, and it's ready now to create a state space representation from this block diagram. We can now do a state space representation. Meaning, let's build or rewrite our first one, x1 prime. x1 prime is now right there. That's the output of that rightmost summing junction, and that's going to equal a combination of u and y, but luckily in this particular diagram y is already x1, and we want our derivatives of our states to be linear combinations of our state variables and our input, and it's right there in front of us. x1 prime is now going to be this signal plus this signal plus that signal. And if we write that down, we now have x1 prime is minus a sub 2 x1 of t, where x1 of t is y. We have plus x sub 2 of t. That's the horizontal signal coming in to that summing junction. And then we have the signal coming down from above, which is a scaled input, or plus b sub 2 u of t. Hopefully you see that now the output of that summing junction, x1 prime, is this combination of three signals, a scaled x1, x2 without any scaling, and a scaled u, to produce this first equation. If we do the same process on the middle integrator, input, which is x2 prime, we again have three signals making up x2 prime. We have minus a1 x1 of t. Then we have the horizontal signal, which is x sub 3. And the signal coming down is our scaled input, which is b sub 1 u of t. We're almost done. We're trying to work our way from the right all the way to the left. We now simply need to express x3 prime in terms of the signals coming in to that summing junction, where x sub 3 prime is a signal coming out. Or x sub 3 prime of t is now equal to minus a sub 0 x1 of t, that's the scaled output, plus a b sub 0, maybe I'll just go ahead and put that over here so that it's clear that it's the input and we didn't have another state variable coming in horizontally. And here are the equations that we have. The other thing that we can identify is immediately we can write down our output equation y of t. That's the same as x1 of t. And now we have our state space representation, maybe not in matrix form, but in equation form. And this particular state space representation is labeled as input feed forward. This is now our input feed forward state space representation. We can build it up as a matrix. We have a state vector that has 3 components or 3 rows, and we want to differentiate each of those components once on the left of the equality. Then we have our system matrix, which you know is always square, and I'm suppressing the arguments, which are t's. Then we have our input matrix, and in this case we only have one input, so our input matrix is a column vector with 3 rows. Let's now fill in the 9 entries in our system matrix, or the A matrix. Here is our A matrix, or the system matrix. We can build the first row by looking at the x1 prime equation. We need to scale x1 by minus a sub 2. We need to scale x sub 2 with a 1. That's right here. And we need to scale x sub 3 in that first equation. X sub 3 is not there. That's now a 0. We do have an input term for a generic A's and B's that we've provided for our transfer function description, and so the top row of our input matrix is B sub 2. We can do the same process for x2 prime. We scale x1 by a sub 1, or minus a sub 1. In this second equation, we do not have an x sub 2, and we do have 1 scaling x sub 3, and we have a scaled input scaled by b sub 1. Our last equation in the system dynamics is now minus a sub 0, x1, no x2, no x3. It does have a scaled input, which is b sub 0. And this is now our B matrix, and that we've called our input matrix. We can now produce our output equation. We only have the one output. We have 3 state variables, which means that our output matrix C is going to be 1 row tall and 3 columns wide to be compatible with the output Y and the state vector X. We have our direct feed through matrix D, and that also needs to be 1 row tall and 1 column wide. This is now our D matrix, or the direct feed through matrix. And we want to now pull off all of the terms that are contained on the right-hand side, or the linear combination of state variables and inputs that make up Y. We only have one state variable, that's x sub 1 with a leading coefficient of 1. So we have x sub 1, no x sub 2, no x sub 3, and no u. And you can now see that in our original transfer function, which was going to now be something that we're going to look at as an example, but now in this transfer function that we started with a b2, a b1, and a b0 for s squared s and s to the 0 in the numerator. We had s cubed, etc. in the denominator with a coefficients. Now wherever you see those b's and a's, they will appear in this input feed forward state space representation. You can see that our a's go into the system matrix in a particular order or a pattern. We have on the upper diagonal, or one up from the diagonal, we have ones that are going on that upper diagonal, and everything else is populated with zeros in our system matrix. Our output matrix is full if we had all of those coefficients in our numerator, and the output matrix and the direct feed-through matrix, or direct input feed-forward matrix, is now this very specific structure of 1, 0, 0, 0. Let's look at an example of how you could go directly from a transfer function. Suppose that I give you 0s squared plus 4s plus 6, and then I have s cubed plus 0s squared plus 7s plus 12. The first thing you want to look for is to make sure that the transfer function is strictly proper, meaning that the numerator order is strictly less than the denominator order, and it is. And we want to make sure in this transfer function that the leading coefficient on our denominator has been normalized to 1, or that it's monic. So in this case, we didn't ever label an a sub 3, but it is there, and it's a 1. We can then see that we have an a sub 2 is 0, our a sub 1 is 7, and our a sub 0 is 12. Our b sub 2 is not going to be there, it's 0. Our b1 is 4, and our b sub 0 is 6. And with those particular labelings for the A's and the B's, we can now immediately jump to our state space representation. It's now a third order. Our state vector is x1, x2, and x sub 3, which is differentiated one time on the left, and I just labeled it as x prime, plus our input matrix times u. Y is now this row vector times our state vector, x1, x2, x3, plus a direct feed-through matrix 0. But now we have what is a sub 2? It's actually 0. So we had minus a sub 2, we had minus a sub 1, we had minus a sub 0, and we put in the pattern 1, 0, 0, 1, 0, 0 to complete the A matrix. Our B's now, we didn't have a B2, we had a 4 for B1, and we had a 6 for B sub 0. And our output matrix for this input feed forward state space representation is just 1, 0, 0 with the direct feed through of 0, since we had a strictly proper transfer function. And I'm hoping that it's clear that once you have a transfer function given, you can immediately write down its state space representation without having to go through creating the differential equation, the block diagram, and labeling the block diagram, and then coming up with the state space representation. Although you could do that. But now you can simply immediately go from G to a state space representation. Cheer 1 will go from, and that would be a way to check your work, is to now use this A, B, C, and D to create G using Cheer 1. As I promised at the beginning, let's now look at what would happen if somebody gave you a slightly different transfer function, and it's now 4s cubed plus 2s plus 5 all over s cubed plus 6s squared plus 7. And what I hope that you remember is to immediately, the first step is to check the orders or the degree of your numerator and denominator polynomial and make sure that you have a strictly proper transfer function. In this case, this is a proper transfer function, meaning the numerator is the same order as the denominator, and we now can't immediately progress from this transfer function to a state space representation. What we need to do is divide, do some long division, and get a remainder that has a numerator that is an order less than the denominator order. So if we go back to our high school algebra class and do long division, we now have 4s cubed. We're missing an s squared, so I'll just sort of leave space for that, plus 2s plus 5. That's our numerator. And now we can perform the long division. We know that a 4 times the denominator will give us what we need in the numerator, so we now have 4s cubed plus 24s squared plus 28. And if we subtract that out, we now have eliminated that highest power of s, and we now have minus 24s squared plus 2s minus 23. We now have a expression for g of s. G of s is now 4 plus a minus 24s squared plus 2s minus 23 all over s cubed plus 6s squared plus 7. This particular part of our expression is strictly proper, and we know how to deal with that. We know how to put that into a state space representation, or the A, B, and C. And this piece right here is actually our direct feed-through term from the input to the output. Now, an input U gets scaled immediately by 4 into our output, and so this is now going to be our D matrix, which is 4. Which means that we now can look at taking into our state space representation, we can build the A, B, C, and D. The A, B, and C from the strictly proper part, and the D from the long division step, which now allows us to say that we can say, oh, we have x1 prime, x2 prime, x3 prime, equal to a square matrix, that's our input matrix, times x1, x2, x3, plus our input matrix u of t, and now we have our output y of t, which will be a little different. It's going to be x1, which is now our 1, 0, 0, plus our direct feed-through matrix 4 times u of t. And how do we build the system matrix, the A and the B? Now we have, here's A sub 2, A sub 1 is missing, and here is a sub 0. This is our b sub 2, and make sure we keep track of the sign. Here's b1, and here is b sub 0, which means we can now write down a sub 2 with a minus sign in the 1, 1 entry. We now have minus whatever that was, which was 6. And we have x sub 2, 0, and b sub 2 is minus 24. That's our first row. x2 prime is going to be made up of a sub 1 with a negative sign, and a sub 1 was missing, so it's 0, plus x sub 3, and then a b1, which was 2. And our final row is now going to be minus a sub 0, which is minus 7, no x2, no x3, and our b sub 0, which is minus 23. You now have seen then that this proper transfer function, which has the same degree numerator as denominator, we needed to get rid of that like order, and we did that by long division. Once we divided one time, we now have a remainder. Here is our remainder of one step of long division. That remainder now is our new numerator that's now 1 degree less than our denominator. We can pull out the 4. That's a part of our transfer function, but it's all by itself, 4 plus this strictly proper transfer function, and we know how to take that strictly proper transfer function into an ABC in our state space representation, and our D is going to be in our direct feed-through matrix, which is in our output equation, and that provides then that 4 scaling U directly into our output Y. And I hope then that it's clear how you can immediately go either from, let's say, this highlighted yellow into this piece, and the other piece is coming to us from our direct feed-through term. If we didn't have, or if we had a strictly proper transfer function, which is what we started with here, even if b sub 2 was non-zero, that would now be going into this equation, and we could still handle that. We wouldn't have to worry about long division. We could immediately write down by inspection this state space representation. If we did have an a sub 2, if this particular value was there, then it would go right there with a change of sign. We now have looked at how we can go from transfer function to differential equation to block diagram to state space, and now with what we've derived, you can bypass those two intermediate blocks and go directly from a transfer description to a state space representation. And next time we will talk about a different way to go from a transfer function to a state space representation, which will be a little bit different, but again, it's going to be a state space representation. I'll see you then.